Some compounds with different molecular formulas have the same relative molecular mass to the nearest whole number. A dicarboxylic acid, so we have two of these, has a relative molecular mass of 118 to the nearest whole number. Deduce the molecular formula. So the first thing we need to do is find out what two of those equals. So we've got 12, add 16, add 16, add 1. So that's 45 times 2. So that's 90. So let's do 118 minus 90. We see that we've got 28 left. 28 would be C2H4, because 2 C's is 24. So C2H4 and then 2 lots of this. So we want it as a molecular formula. So we've got 4 C's in total, 6 H's and 4 O's. A student dissolved some of the carboxylic acid from 10.1 in water and made it up to 250. In a titration, 25 of this acid solution that was 250 is needed to neutralise 21.6 of 0.0 molar sodium hydroxide. So remember that this is a dicarboxylic acid, so it's like a H2A, so that would need 2 NaOHs to neutralise it because there's 2 acid groups to give us Na2A plus 2 H2Os. So let's do number of moles of NaOH from our values. 21.6 centimetres cubed into decimeters cubed times 0.109. If we do that on our calculator, we get 2.3544 times 10 to the minus 3 moles. So the number of moles of our dicarboxylic acid would be half of that. Is 1.177 times 10 to the minus 3. But that's in our 25. In our 250 flask, there's twice as much. Not twice as much, 10 times as much. And then mass is Mr. Moles. We know the MR because we had it up here, 118. If we multiply those, we get 1.39 grams. Compounds with molecular formula C6H14O2, so that's a 2N plus 2 type formula, so saturated, no double bonds, also have a relative molecular mass of 118 to the nearest whole number. These include the diol shown. Deduce the number of peaks in the 1H proton NMR spectrum of this diol. So how many different types of hydrogen have we got? So it's symmetrical about this midpoint, so we only need to look at 1/2. So we've got the OH, we've got the CH3s, we've got this H, and then we've got one more type. We just get a different colour pen, which I don't seem to be able to do. This type here. So it looks like we've got 4 different types of proton. Draw the structure of a different diol that has 1H that consists of 2 singlet peaks. So 14 H's, only 2 types, all the same. And remember that the OH is 1 type, so all the hydrogens that are not on the OHs, so the OHs are identical to each other, that has to be one of the types, which means the remaining 12 H's are all identical. So we've got 4 CH3s that are all identical. If we went like that, and we just count up 1, 2, 3, 4, 5, 6 C's all together, yeah, this would work. All the CH3s are the same, and then the OHs are the same, and there'd be singlets because there's no hydrogens on these central carbons. The dicarboxylic acid in 10.1, Oops, just go back to 10.1. Okay. C4H6O4, and the isomers in questions 10.3 and 10.4 all have the relative molecular mass of 118. State why the dicarboxylic acid can be distinguished from the two diols by high resolution mass spectrometry using electrospray ionisation. The electrospray ionisation part is not really relevant. The point is it's high resolution mass spectrometry. So since molecular formulas are different, the precise MR will be different. Isomers would not be distinguishable, but because these two things are not isomers, they would be different to more decimal places.